Hi everyone, welcome back. Just a quick reminder that in this channel, I post videos about statistics, machine learning, and data analytics. This is one of my videos about statistics. I will show you how to do a multiple linear regression analysis in R using the best subset selection method. As usual, I prepare a notebook for this video, and I will share a link to this notebook in the video description. So you're going to have access to all the code that I'm going to use in this video, all the interpretations, all the comments, okay? So don't worry about that. Now, this video is a continuation of another video I have on my channel titled Preliminary Correlation Analysis, where I illustrate how to do the correlation analysis that we are supposed to perform before starting a regression analysis. So, if you're interested in understanding how to do a correlation analysis in R, you should definitely check out that video. But in this video, we're going to focus on regression only. All right, let us get started. This is the notebook that I prepared for you guys. And in this notebook, I actually included all the material from video one. So in this notebook, you're going to have both video one material and video two material, okay? But let's go ahead and scroll down to the video two material because we don't need to go over this again, the video one stuff, right? So let's find the video two material. And here we are, all right? Here we are, guys. Let's first take a look at the data frame that we are using to apply regression. And the data frame is this one, credit DF BSS, best of the selection, update one, okay? This is a data frame with data about 400 observations, specifically people, so 400 people. And from each person, we have information about his or her income, the credit card rating, the number of credit cards, the person's age, so on and so forth. And finally, the balance. The balance is the credit card balance, okay? Credit card balance. So as you can see, we have information about people's financial information and also some demographics, okay? And what is the problem that we're facing here? Well, we want to obtain a multiple linear regression model to predict balance. So balance, credit card balance, will be the outcome or target variable. But in that regression equation, we want to include only predictors that meaningfully improve the model's predictive performance. So we don't want to include all the predictors, or we don't want to include unnecessary predictors. We want to include only predictors that give us something from a predictive point of view, okay? All right, how do we tackle this problem, guys? Well, when you want to obtain a good multiple linear regression equation, and this is what we want, to obtain a good multiple linear regression equation, you can actually apply two approaches. You can apply the machine learning approach, or you can apply the statistics approach. In the machine learning approach, we separate the data used to obtain the model from the data used to evaluate the model's predictive quality, okay? But in the statistic approach, we don't do that separation, okay? So that's the main difference. So in the machine learning approach, we separate the available data into two data sets, the training data set and the test data set. With the training data set, we obtain the model, and with the test data set, we evaluate the quality of that model, okay? That's the machine learning approach. In the statistic approach, we don't separate the original data set into two. No, we use all the available data to both obtain the model and to evaluate the quality of the model. But we make sure that to evaluate the quality of the model, we use metrics that adjust for overfitting. So that's the key feature of the statistic approach. So to evaluate the quality of the model, we use metrics that adjust for overfitting. So in the machine learning approach, we kind of adjust for overfitting when we separate the two processes. So by separating the two processes, we make sure that we kind of detect models that overfit, okay? But in the statistic approach, since we don't split the data into training and testing, since we don't separate the two processes, we adjust for overfitting by using metrics that account for overfitting, okay? What metrics account for overfitting? many metrics. For example, adjusted R square, residual standard error, the CP statistics, BIC, Bayesian information criterion, and many others, okay? In this video, we are going to use two of those metrics, adjusted R square and residual standard error, okay? So in this video, we're going to actually use the statistic approach, okay? So we are not going to use the machine learning approach in this video. We're going to use the statistics approach, and I'm going to illustrate the statistic approach using two metrics, adjusted R square and residual standard error, all right? Okay, let's go. To actually obtain this, guys, as you probably saw in the title of the video, to obtain the multiple linear regression model, we are going to apply the best subset selection method, okay? Let's do that. Actually, let's first apply the best subset selection method based on adjusted R squared. And then later, we're going to apply the best subset selection method based on RSE, okay? Okay, so to apply the best subset selection method in R, we can use this function, regsubsets. Now, this function is part of the libs package. So the libs package is an external package. So to use it, we need to install it. So that's what I'm doing in this code cell, okay? In this code cell, I'm installing the libs package, okay? I already did, so I already installed the package, so I'm not gonna install it again. But if you want to use my notebook to practice all of this, you need to remove the comment from that line of code, all right? And then you need to execute that code cell. You need to run that code cell to install the package, okay? I don't have to do it because I already did it, so that's why I'm gonna comment it out, okay? After you install the libs package, you need to load it. And remember, to load a package, you need to load a package, you need to use the library function and then the name of the package, okay? So let's go ahead and load the libs package. Let me run this code cell. Done. So package is loaded. And now let's go ahead and apply the regsubsets function. Remember, this is the function that allows us to apply the best subset selection method, okay? Here it's where I am applying the regsubsets function, okay? And that function takes 3 arguments, okay? I'm going to explain the second argument first because it's the easiest one, okay? So the second argument is just, defining what is the data. So what is the data frame you're using to apply this function, okay? And the data frame we are using is the one I showed you earlier, the credit df bss update 1, okay? That's the first argument. The second argument is, that's the second argument. The first argument is actually this one, okay? That right there is an expression that defines both what is the outcome variable and what is the predictor or predictors, plural. In this case, plural because we're doing multiple linear regression. So that is an expression that defines both things, the outcome variable and the predictors. Here, the way you write that expression is you need to use the tilde symbol. That's the tilde symbol. And before the tilde symbol, you define the column from your data frame that represents the outcome. Here we're saying our outcome variable is balance. Okay, this column right here, balance. That's our outcome variable. Then you use the tilde symbol, and then after the tilde symbol, you define the predictors. But here, after the tilde symbol, we see a dot. What does that mean? That's a shortcut to tell R that for the predictors, we want to use all the columns. So when you use a dot, that means that you want to use from the data frame all the columns as predictors. Okay. So this is the outcome, but any other column, it's a potential predictor. Okay. So that's a kind of easy and quick way of defining that, instead of, because the alternative is to type in the name of each predictor separated by a plus sign. So that's a lot of work. Okay. So that's a nice shortcut. Perfect. And then the last argument is this. The last argument is the argument that you need to pass to the MV max parameter. What is that MV max parameter? That is the maximum number of predictors that we want to consider to be part of a model. Okay. In this case, what we are saying is that the max number of predictors that we want to consider to be part of a model equals the number of available predictors in the data set. And in this case, the number of available predictors is 8, okay? So we're saying MV max equals the number of columns in the data frame, 9, minus 1, 8, okay? 8. So we're saying again that the max number of predictors that we want to consider to be part of a model equals 8. And what does that mean? It means that when we apply the best subset selection, the best subset selection method will try models, many models of size 1, many models of size 2, many models of size 3, dot, 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 until a model of size 8, with a model with 8 predictors. So that will be the maximum number of predictors considered in a model, okay? That's what that means. We cannot try, a model of size 9 because, we don't have 9 predictors, okay? So that's the max that we can try. All right, so notice that I am storing the output from reg subsets in this variable, best subset balance. Now, the recommendation is that instead of exploring the output from this directly, the recommendation is that we invoke the summary function on that variable. And that's what I'm doing in the next code cell. So I'm invoking the summary function on that variable. And then the recommendation is that we store that in a new variable. That's what I'm doing. So summary, I'm invoking summary on that variable, and then I am storing that in a new variable, okay, which is same name, but with the word summary added. So best subset balance summary. And then now the recommendation is that we explore the output from this. We explore the output from that variable, okay? All right, let's do that. Actually, let me execute this code cell, which I did not do. So let me execute this code cell and now this one, okay? Cool. Now let's go ahead and explore the output from this, okay? The output from that variable, okay? And as you will see, let me execute this. We're just exploring the output from that variable. As you will see, here we're going to be able to find out the best equation of each size. So the output from that variable gives us the best equation of each size, all right? What do I mean by that? Okay, let's take a look at the output. And actually, I'm going to ask you to focus on the last part of the outcome only, okay? That's the most meaningful part in terms of, from an interpretation point of view. That's a matrix. That last part is a matrix, okay? It's a matrix with 8 rows, okay? It has 8 rows, all right? Well, what is this giving us? All right. Row 1, okay? Row 1 is telling us what predictor to use if we want the best equation with a single predictor. Row 2 is telling us what 2 predictors to use if we want the best equation with 2 predictors. Row 3 is telling us what 3 predictors to use if we want to get the best equation with 3 predictors, and so on and so forth, okay? But how do we actually interpret this output for this problem? Well, what you do is for each row, okay, for each row, you look for the column with an asterisk, okay? So for each row, you look for the column or columns with an asterisk, okay? And that will tell you the best best predictors to include for each equation, okay? So let's take a look at the first row. The first row, I highlighted the first row. Where do you see the asterisk? At what column do you see the asterisk in the first row? Here, a rating, okay? A rating. And what that means is, if you want an equation with a single predictor, that single predictor should be rating. So rating will give you the best equation of size 1. How about row 2? Row 2. Where do you see the asterisk in row 2? The asterisk are at income and rating. That means that if you want the best equation of size 2, you need to use income and rating as predictors, okay? How about row 3? Where do you see the asterisk at row 3? The asterisk are at income, rating, and student yes. Remember that student yes it's binary variable that takes a value of 1 when the person is a student and a value of 0 otherwise, okay? So this is telling us that if you want the best equation with 3 predictors, you need to use income rating and student yes, okay? So that's the information that this output is giving us. And, this is great. This is great because, we have 8 good equations. So we have the best equation of size 1, the best equation of size 2, the best equation of size 3, perfect. But we only need one equation. Remember our goal. our goal is to find a good multiple linear regression equation. So we don't need 8 equations. We only need one. So what we need to do now is we need to compare these 8 equations and select the best one among them. And that's the use of adjusted R squared. We're gonna use adjusted R squared to compare these equations and select the best one. Okay, and that's what we do next. Okay, compare the best equations of each size and select the single best one. Okay, let's read what I wrote for you here. Now we need to decide what is the best among the 8 possible equations suggested in the previous output. Okay, we use adjusted R squared to compare these equations and make this decision. By decision, I mean selecting the best one. Okay, and that's what we do to get adjusted R squared for each of the 8 equations. We do the following. From that variable, the variable that I used earlier, we can retrieve this attribute, adjusted R squared attribute, and that will give me the adjusted R squared for each of the 8 equations. Okay. Then what I did was I rounded the adjusted R squared values to 4 decimal places for easier interpretation, and then I store the adjusted R squared values in that variable. Okay. Let's run it and print it out. And there we have it. Okay. So what is this value? 0.7452. 0.7452 is the adjusted R squared for the best equation of size 1, the equation that only has rating. This 0.8745, that's the adjusted R squared for the best equation of size 2, so the equation that includes rating and income, okay? And so on and so forth. Now notice that it's kind of now a little bit difficult to map the adjusted R squared values with the predictors attached to that value. You know what I mean? Like this is, I don't know, this is the adjusted R squared for the best equation of size 5, right? That 0.95. That's the adjusted R squared for the best equation of size 5. If we want to know what are the predictors that correspond to that equation, then we need to go up and then find in row 5, where do you see the asterisk? So that process is a little bit inconvenient, if you will. So what I'm going to do now is I'm going to create a data frame that summarizes the predictors and the corresponding adjusted R squared. Okay, so I'm going to create a data frame with 2 columns. Okay, column 1 will show us the predictors that form the best equation of each size, and then column 2 will give me the adjusted R squared for the best equation of each size. Okay, and that will be easier for us to interpret. Okay, and to that, first I get this to create that data frame, I first need to get this matrix. And in that matrix, what happens is for a given row, we see a true value for the columns selected to be part of the best equation of each size. So in row 1, we see a true where for rating, because rating is the best, is the predictor for the best equation of size 1, right? In row 3, for example, we see true values where we see true values for income, rating, and for student yes, because these are the predictors, the 3 predictors that you need to use for the best equation of size 3. Okay, perfect. Now what I do is I use this matrix. Okay, and with the following code line, what I do is I select the names of the predictors with the true value in this matrix. Okay, I select the name of the predictor with the true value in this matrix. Okay, and sure enough, let's execute that and take a look at the output. And as you can see, we're able to retrieve the names. So the name of the predictor in the equation, or the best equation of size 1, the name of the 2 predictors in the equation of size 2, in the best equation of size 2, and so on and so forth. Okay. Now we're able to create the data frame that I mentioned earlier. Okay. And that is that data frame where column 1 will be the predictors in the model, and then column 2 will be the adjusted R squared. Okay. Now let's take a look at this, and that's it. Really, really nice summary, guys. Okay. So the best equation of size 1 is the one that includes rating, and this is its adjusted R squared. The best equation of size 2 is the one that includes income and rating, and this is its adjusted R squared. So nice. So now we're cooking, right? Excellent. Now we need to compare these 8 equations. How do we compare them? Well, we're going to compare them using the most widely used criterion, but this is a criterion that is somewhat naive, okay, and simplistic, but that's okay. This is kind of the book criterion. So if you read a book about how to apply best subset selection using adjusted R-squared, this is what they're going to tell you. They're going to tell you that you should select um, you should find out where adjusted R squared stops increasing, okay? And where adjusted R squared stops increasing, that's the moment where you do the cutoff, because after that, adding more predictors will not give you any improvement in performance. Okay, so find where for what model adjusted R squared stops increasing, and then that's your cutoff. So you don't add any more predictors after that, because after that point, the predictors that you add de decrease adjusted R squared, and that's a bad sign. Okay, that's a bad sign. That's a sign that those predictors are kind of noise. Okay. Um, so actually, what we need to find out is where, like, at what size? At size 1, size 2, size 3, size 4, size 5. At what size the adjusted R squared stops increasing? Okay, and to do that, we can use this function wish max. Okay, wish max will give me the row at which adjusted R squared reaches its maximum. Okay, because guys, stops increasing means where adjusted R squared reaches its maximum, right? So where adjusted R squared reaches its maximum, it stops increasing. So same thing. So this function will give us that place where adjusted R squared stops increasing. Okay, and I'm gonna apply wish max to this specific row. I'm sorry, to that specific column from the data frame, adjusted R square model. Remember that is this column, adjusted R square model. Okay, and I'm going to store that in this variable best model index. And then sure enough, that will give us 5, 5, 5. Is that correct? We can check. Well, 5, that is that model right there, the model of size 5. Is the model of size 5 the one with the highest adjusted R square? Yes, it is. Because after that, then the adjusted R square stays the same. So it stops increasing, okay? So it's true that that the model of size 5 is the one that gives us the maximum adjusted R square. After that, adjusted R square does not increase anymore, okay? Okay, so that's good. Now what I'm going to do next is I'm going to use that index 5, to retrieve the names of the predictors. So I want to be able to retrieve the names of the predictor part of the model of size 5, okay? That's what I do next. And that's what I do next here. Okay, use this index to get the names of the predictors part of the model where adjusted R squared reached its maximum. Okay, so I'm going to use that index to index the predictors in model column. The predictors in model column is the first column in the data frame. Okay, and sure enough, I get the name of the 5 predictors. Okay, and then the last thing that you should do is retrieve the coefficients, because you don't want the predictors only, the names of the predictors. You want the coefficients as well, because our goal is to propose a regression equation. A regression equation is the intercept plus each predictor times its coefficient, right? So we need the coefficients of the of each predictor in the equation. Okay, and to get the coefficients, we can use the coef function. Okay. And for the coef function, we need to use 2 arguments. First, the best subset balance variable that we defined earlier, and the index for the best model, okay, which is 5 in this case. All right. And sure enough, we get the coefficients of the regression equation with the 5 predictors that we chose. Okay. Income, rating, age, student yes, and married yes. Okay. Income, rating, age, student yes, and married yes. Okay. And the corresponding coefficients, and also the intercept. Okay. This is your kind of your final kind of your proposed solution. So you can say that after applying best subset selection based on adjusted R squared, your proposed regression equation is this one. Okay, that's a regression equation that supposedly includes only good predictors. Okay. All right, perfect. So now what I'm going to do next is I'm going to show you how to apply best subset selection, but based on residual standard error. So instead of adjusted R squared, based on residual standard error. Okay, let's do that. just a reminder that this is the formula of the residual standard error. I'm showing you the formula because unfortunately, R does not give us RSE. Like when we apply best subset selection, R does not return RSE. So we need to compute it. So that's why I'm showing you the formula. And as you can see, RSE is the square root of SSE divided by n minus p minus 1, where SSE is the sum of the square of errors, n is the sample size, number of observations, and p is the number of predictors in the equation that you are considering. Okay, p is the number of predictors in the specific equation that you are considering. Okay. What you see inside the square root is the variance of the predicted values, okay, around the real values. And by that, I mean the predicted values of balance. Balance is the outcome variable, right? So this quantity that you see inside the square root is the variance of the predicted values of balance around the actual values of balance, okay? And since RSE is the square root of that, RSE is a measure of the standard deviation of the predicted values of balance around the real values of balance, okay? Now, RSE is a metric, as I said earlier, that adjusts for overfitting. Why? Notice that RSE is the division between SSE and this quantity, n minus p minus 1. Guess what? If you add more predictors to an equation, okay, if you add more predictors to an equation, SSE decreases. The sum of the square of errors decreases for sure, okay? But also at the same time, if you add more predictors to an equation, P increases, so n minus P decreases as well. So what is happening is that when you add more predictors to an equation, the numerator decreases, but the denominator also decreases because, as I said, n minus p decreases. So it's kind of when you add more predictors to an equation, what happens is a tug of war where the numerator is decreasing, but the denominator, the bottom, is also decreasing. So what's going on? What is going to be the end result? Will RSE decrease or increase? Because you have both the top and the bottom of that fraction decreasing. So what is going to be the end result? Is RSE is gonna show a decrease or an increase? Okay, that's what I said. Like when you add more predictors, it's like kind of a tug of war. Okay, and then what happens is that if the predictors that you are adding are useless or kind of noise predictors, the end result is that RSE is going to increase. So when you add more predictors, RSE only decreases if those predictors are good predictors that are actually giving you something positive from a predictive point of view. Okay, so that's why RSE is a metric that I just for overfitting because it will increase. It will increase when you add predictors that are bad predictors, which signals that those predictors are not good. So whenever you see RSE increasing, that's a sign that the predictors that you're adding are not good enough. Okay. All right. Perfect. Now, as I said, when we apply best of selection based on the regsubset function, we don't get RSE, but that's fine. We're gonna be able to compute RSE. So I'm gonna apply a formula to compute RSE following this exact formula. Okay. Now, one clarification, guys. This is what I wrote here for you. In R, they do not use the term SSE. So they don't call SSE sum of square of error. They use the term RSS, residual sum of squares. They are the same thing. So sum of a square of errors or residual sum of squares, same thing. So SSE is the same as RSS, okay? But in R, they don't call it SSE, they call it RSS, okay? Why am I telling you that? Because you will see that R does not give us RSE, but it gives us RSS or SSE. And once we have SSE, it's very easy to get RSE using this formula. Okay. All right. Again, what we need to do now is, we have the best equation of each size. So we need to get the RSE for each of those 8 equations and compare them based on RSE. Okay. To compute RSE, I'm going to start by creating a vector with all the possible number of predictors. So we are considering predictors from 1 to 8, right? 1 predictor, 2 predictors, 3 predictors, 8 predictors, right? So I'm going to create a vector to store those numbers, okay? Number of predictors from 1 to 8, okay? And now I'm going to create an expression to compute the RSE for each model, okay? This variable RSE or all models is going to store the RSE for each of the 8 models. So the RSE for the model, for the best model of size 1, the RSE for the best model of size 2, and so on and so forth, okay? And notice that, what am I doing here? Well, this is just the square root, okay, as the formula that I showed you earlier. The square root of what? The square root of this, that's the top, divided by this, that's the bottom, okay? What is the top? From the variable stored in the summary, we are retrieving this attribute, RSS. What is RSS? SSE, right? That's what I told you here, okay? R RSS is SSE. So we're able to get the top, SSE, okay? And now we are dividing that by what? By this quantity. What is that quantity? The number of rows in the data frame, that's n, the sample size, minus the number of predictors minus 1. That's exactly the formula that I showed you earlier, okay? And then doing that will give us the RSE for each model. So this is the RSE for the best model of size 1, the one that includes rating. This is the RSE for the best model of size 2, the one that includes rating and income, so on and so forth, okay? Now we need to compare these RSEs and select the best one, okay? But before doing that, let's kind of put together the predictor names and the RSE in a data frame as I did earlier with adjusted R-square, okay? That's what I'm doing next. That's the nice summary data frame with the predictor names and their corresponding RSE. Okay, guys, so how do we decide based on RSE? How do we compare these models based on RSE? For RSE, we are not looking for the highest RSE, the opposite. We're looking for the lowest, okay? RSE is the residual standard error, prediction error. So for the prediction error, we want the lowest possible, okay? So for RSE, we're looking for the model at which RSE stops decreasing. So we're looking for the minimum, okay? We're looking for the model at which RSE stops decreasing. So we're looking for the minimum, okay? And to that, we can use the wish mean function, okay? So I'm applying the wish mean function to the RSE model column, this one. All right. And sure enough, we're going to get that the minimum RSE happened at index 7, okay? Is that correct? Let's check. Index 7, that will be that model right there. Is that the lowest RSE? Yes, it is. So notice that before that we have 107, 102.78, 86. After that we have 102.78, 78. So a slight decrease. But then after that we see an increase, 102.91. So yes, it's true that the lowest RSE happen at this model of size 7. Okay. So at this point, what we need to do is just retrieve the names of these predictors. Okay, so using the index, we can retrieve the names of the predictors. Okay, with this code cell right there. Those are the 7 predictors, and then what we need to do is, as I told you earlier, not only the names of the predictors that form the equation, but also their coefficients. Okay, and those are the coefficients for those 7 predictors. Okay, so again, what you conclude here is, after applying best subset selection based on after applying best subset selection based on RSE, the proposed solution, the final regression solution, is the one that includes these 7 predictors with these coefficients. Okay. Now, notice that there is a kind of discrepancy, right, between RSE and adjusted R-squared. Our adjusted R-squared told us that we needed 5 predictors, but RSE is telling us that we need 7. What's going on? What's going on, guys, is that, as I told you earlier, we are using the book criterion to select the best model. The book criterion is very simplistic, very naive. It says, oh, the best model is the one that gives us the highest adjusted R squared. And for RSE, the book criterion is the best model is the one that gives us the lowest RSE. That is very naive. If we used a non-naive approach, which we are not going to do, okay? Because this video is to show you the basic application of best subset selection. But if we used the um, non-naive approach, and there are many non-naive approaches, we probably get the same equation with both RSE and adjusted R square. Okay, so again, if we used a non-naive approach, okay, we probably get the same equation with both adjusted R squared and RSE. And probably that equation is, I have done it. Actually, I have done it. I have applied best subset selection with the non-naive approach, and the best equation is actually the one that includes these three predictors only. Okay. Income rating and student yes, which makes sense. Notice that the decrease in RSE after that is very, very small. So when we add age, so when we go from income rating student yes when we go from income rating student yes to income rating student yes and age, guys, the decrease is from 103.31 to 102.90. So slight decrease, okay? Slight decrease. And if we look at adjusted R square, same thing happens. Let's take a look at adjusted R square quickly. Look, when we go from income rating student yes to income rating student yes and age, the increase in adjusted R square is so tiny. It's 94.95 to 94.99. So it's like a 0.004 increase. 0.004. Okay, that's 0.0 that's 0.04% increase. Okay, so very, very small, guys. Very, very small increase. So as I said, if we used a non-naive, non-simplistic approach, probably both adjusted R square and RSE will point to the same equation, and that equation is this one. Okay, again, I have applied best subset selection using non-naive approaches, and the solution is these three predictors. Okay, but again, guys, my goal with this video was to show you the basic application of best subset selection using the naive approach. Okay, and again, the naive approach is not necessarily wrong. Actually, as I said, it's the book approach. Is the approach described in most books. Okay, so it's not wrong. It's just a little bit simplistic and naive. Okay, but definitely you can apply. So you can apply it like that. So you can apply best subset selection using the naive and simplistic approach. Okay, because again, it's just the kind of standard approach. Okay. All right, guys, that's all for this video. I hope you enjoyed. I hope you learned how to apply best subset selection in R. Thank you for watching, and I will see you in another video. Bye, guys.